streaming again, so don't be too crazy.
Oh, you're streaming again?
Yeah.
Oh, sorry.
No, you can talk. I don't care.
There might be me screaming randomly in the background. There might be me screaming randomly in the background. There might be. I'm telling you.
Alright, we're gonna do this problem again. I want to see it. Alright. Given two integer arrays, preorder and inorder, where preorder is the preorder traversal of a binary tree and inorder is the inorder traversal of the same tree, construct and return the tree. So we are given this binary tree. 3, 9, 20. And we're given the preorder and inorder. Preorder is the current, then left and right. So this would be 3, 9, 20, 15, and 7. That's the preorder, and then in order would be left, middle, right. So it'd be 9, 20, 15, 7. Oh, sorry. It'd be 9, 3, 15, oops, 20, 15. Whoa, brain is off. So it would be left, middle, right, and then we go back to left. So 15, middle is 20, and right is 7. So let's double check to make sure that's right. 1527, yep. So we're going to want this to be a recursive function no matter what. The ideal that I can get to would be O of n time complexity and O of n space complexity, where space complexity... Let me explain the space complexity in a second. Alani! Hey, Alani! Why are you screaming? Hey, come here. Come here. It's okay. So, what I want to do is do a depth first search, visiting each node once to recreate this. That would be ideal. And I want this to be recursive depth first search, where we recreate the tree using these two arrays. Okay. Now, what can we notice about something? First, we know that the preorder will give us the root of each of the next node, right? So the first root is 3, and then we'd call the left, and that would be 9, and then we'd call the right, that would be 20, and then we call the next left, that would be 15, and 7. So this will keep track of our next root. And then, if we notice, right, in this in order, let's take 20 for example. Everything in order. Is that right? In order 9, 3, 15, 27. Yeah. Everything to the left of this 20 is to the left of 20, and then everything to the right is to the right. And then let's look at 3. Everything to the left of 3 is to the left of 3 in the in order. Everything to the left of 15 is to the left of 15 in this in order. So basically, what we can do is for each preorder root, we know we can recursively call this with everything to the left of the 3 in order. And if we're doing this recursively, we would call this preorder, hit X, and then, hey Lonnie. we would somehow need to know how to split this up into the left and right. And basically, everything to the left of this 3 would be what's called in the left recursive call of 3. And everything to the right would be in the right recursive call. And then following that, it would look something like this. And then we would get to 20. Like everything to the left is good, we'd get to 20. And then everything to the left of 20 would be in the left recursive call. Everything to the right of 20 would be in the right recursive call. So then the key becomes, how do I find where this index is in the in order? One thing that we could do is every recursive call, we could just search this linearly to try to find, hey Lonnie, this isn't your food. You can't have this, little cat. We could iterate through this and find the index in each recursive call. Or what we can do is just have a mapping of the in order mapping. That's called the in map. And we would have each number. Oh, Alani. My cat turned off my stream. He's a sweet kitty. So we are back to this, and then we want to go to Excalibur. So we'd have a mapping, right, of the in order elements and their index. So this would be 0, 3, 4. And basically 9 would be 0, 3 would be 1, 15 would be 2, 20 would be 3, and so on. And basically this would allow us to find this index in order right away. Another thing we want to do in this recursive call is we want to determine the left and right of this in order, like what we're actually accessing. We want to do that using pointers instead of recreating the array, because every time we recreate that array and like cut it down, it's O of n. So what I'm talking about is slicing, right? So if I wanted to slice from index 2 to the end, right, 0, 1, that would be 2 to this. This is a cost of 3 because I'm recreating this. So instead I can just have a helper function where I'm just using the pointers themselves. So let's do this. First thing we want to do is create that map, that dictionary for the positions. So I'm going to do it like this. We're going to have the num and I. So we want the num being the key and I being the index for the in order array. And we can use enumerate in Python to get the index and the actual number. So we have this, and then let's have our helper function, which I'm going to call a DFS because that's what we'll be doing. And specifically, we want a left and right pointer. I'm just going to keep this at left and right. And when we actually call it, we're going to return the root that we want to. We're going to return the root for every call to DFS. And so our output will just be the root. Left and right will be 0, and then the length of in order -1. So if this is in order, we're calling it with 0 and 4. And we want to stop when left is greater than right. We want to return none. And yeah, we want these to be null. So we wouldn't do an empty node because that would default 0. We want to specifically return none. Okay. So we're going to have one variable that marks the middle of our in order tree. So this would be middle index. I'll just call this index. Index is equal to the position of num. Now, what is the number that we're trying to get? Well, the leftmost node in our pre-order traversal will always be the new root, right? Right, like, so if I do call it with 3, like if this is my 0 and right, 0 would be 3. And then what would I call it with the next? It would be 0 and 0. And then this would be 2 and 4. So the leftmost position Well, since I know that this is going in order, right? Like I know I'm going here and then going to the left and then going to the right. I know that the way I traverse this is going to match this pre-order. So I can actually just have an index. A class index that will, class variable that will keep track of the current route that I'm at. Specifically, this is the index for pre-order. How do I get... self.pre-index. So this is the position of the in order index. And so once we have this, this is what we need. We can also create our root with our new value. So we can say root is equal to, this is a tree node with our pre-order index. Right, does that make sense? No, because we actually need the number. So we can say the root val is equal to this. And then we want the position of the root val in, this is specifically the in order position. Okay. In order position of the root val, we get the in order index. So then what can we do? We can create a root node with the root val, and then we can set the root.left to be equal to DFS. And then we want to move this. So this left and right pointer is specifically keeping track of what in order elements we have access to, if that makes sense. So we would have it at left, and then we would have it at in order index minus 1. Because if it's 3, we want to search this. And if it's 3 for the right side, we want to search the rest of this. Okay. And then root.right is equal to the DFS no index plus 1, and then right. And then we simply return the root. Now, one thing I have not done is increment the preorder index throughout this. So this is the first time I use it. What I'm going to do is increment this once I have the value that I need. Specifically, we want to do this before we call the DFS functions. Right now, I'm just going through my work, making sure everything matches my expectations. Preorder will be, yep, we get the index. The in-order index is the position of the root value, and I get it using this map. Increment the preorder index, and then I'll call it on the left and right. That looks good to me. Misspelled that. Everything looks good though. Functionally, we are there. Super time efficient. Awesome. And again, this is O of n time complexity and O of n space complexity. We've got container with most water. You are given an integer array height of length n, where there are n vertical lines drawn such that the two endpoints of the ith line are I, 0, and I height. So the two endpoints of the ith line, height of length n. So we're given n heights. Okay. There are n vertical lines drawn. Ith line. Okay, so what they're saying is each line starts at 0, and the height is the value in the array. So we want to return the two lines that together contain the most water. So let's draw this out. So maximum height is 8. Let's draw this graph. So if this is 8, 1, so this is our graph, our chart, and then we have 1, 2, 3, 4, 5, 6, 7, 8, 9 heights. I don't actually need to draw all these out. But the point is, we have some lines here, and we want to return the maximum height, right? If this, if it's between these two lines, this first one and this line, the maximum height is here. So it's the minimum of the two lines. This one is here. It's the minimum of these two lines. But also, what happens if this, we would need to compare these areas, right? And so that's the point. So we're given all these lines. In this case, the max area of the water blue section and the container. Okay, so what I notice about this first example is that well, one, we're going to need 2 pointers to represent the current pole that we're at, right? So we're going to have a left pointer and a right pointer. So we're going to have a left and right pointer. And then let's look at this position. Like if our left pointer is at this height of 1 and our right pointer is at height of 7. Intuitively, what has the most potential for having the largest area? We're going to be checking each position anyway. So what I can do is assume intuitively that this height of 1, well, in this first position, moving either one will decrease the width, right? So we want to decrease the one that gives us the least chance in the future, basically the smaller height. So we would increment the 1 height and then we would calculate it. And then we would compare the 2 heights. Now it's at the second height and the last height still. Okay, which one is the maximum? And we would decrease the smaller one. And we would keep doing that, keep comparing the values, and then the output will be the maximum of that. And we have to check all of them because we don't know. We don't know. Like if 2 heights, we have 2 lines that are like infinity, right? It would be those 2 lines right next to each other that would give us the answer. So the time complexity of this, I would just have to go through this once. So it'd be of n time complexity. And then space complexity, I'm only storing the integer value, so it'd be O of 1 or constant space. So let's code this up. So we have a max area, which will be initially set to 0. And then I need a left and right pointer initialized to 0 and the length of heights minus 1. And then all we do is do while left is less than right. And specifically less than right, but because 2 heights at the same position will not work. So it can't be less than or equal to. At the bottom, we'll return the max area because that is what the output that we will need no matter what. We're not going to know the actual output until we go all the way through. So yeah. Then we can set, at each position, what we can do is set the current max area to be equal to the maximum of the max area and of height L, and then it's, so it wouldn't just be height left times height right, it's the minimum times the minimum of these two, so the minimum of height left and height right times the width. So this would be right minus left plus 1. Because if this is at 0 and this is at 1, no, is that, or is it just right minus left? So 0, 1, 2, 3, 4, 5, 6, 7, 8. They're saying this is, so this is 1, 2, 3, 4, 5, 6, 7, 8. 8 minus 7. So it is just right minus left, because in this case, 0, 1, 2, 3, 4, 5, 6, 7, 8. 8 minus 1, 7. Height is 7. 7 times 7 is 49. Okay, so it's just right minus left. And then, so this is our max area, and we'll get this every single time. That's fine. Then we need to compare the heights. So if height of left is less than height right, we can increment left. Else we decrement right. And I believe that's all that we should have to do. We take the minimum of the left and right height and then multiply it by the width. And that's it. That's all it took. Of n time complexity, O of 1 space complexity. Well, what is the brute force of this? The brute force is just have 2 for loops, and for each position calculate it. But yeah. So we have letter combinations of a phone number. Given a string containing digits from 2 to 9 inclusive, so this includes all of them, return all the possible letter combinations that the number could represent. Return the answer in any order. So, 1 does not map to any letters. A mapping of digits to letters, just like the telephone number, is given below. Note that 1 does not map to any letters. So if we press the digits 2 and 3, 2 can represent A, B, or C. 2 can represent A, B, or C. And 3 can represent D, E, or F. So given the fact that I put 2 first, what I want to do is find out all the combinations. So first, 2 could be equal to any of A, B, and C. And then for each A, B, and C, it could be any of D, E, F. And it's the same for all of these, right? So AD, AE, AF, BD, yep, that makes sense. And if we had another one, let's say 4, which 4 represents GHI, we would have this, GHI. So, first of all, what this is looking like is we'll have n to the 3 combinations, right? Because for every n, we have 3 choices based on this phone number. Unless it's 9. 9 will have 4. But we don't care too much about that. I mean, basically this is how many answers that we'll have. So logically that makes sense. So we want letter combinations. It's specifically not permutations because what we want to do is go through each of these. First of all, I want to have a map, right? I'm going to have a dictionary mapping each digit to the letters that represents. So I would have this be A, B, C, because then I'll be able to loop through these. And then the next one, 3, that would be D, E, F. And then what do I need to do? I need to have an index keeping track of the number that I'm at. So like if this is my input, I need an index that represents this. So we've got I, and then we got the next one, and then we got the next one. And so the simple thing that comes to my mind is a for loop, right? We go through each character at index I, add it to the output, and then call another function, call the function recursively with I incremented. And then call another function recursively with I incremented. So what does that actually look like? It means for each letter n, well, we loop through this n times, and then we call it with n minus 1, and then we call it with n minus 2, and then we call it with n minus 3, right? So this looks like n factorial. And let's see. So 3, 4, 5, 6, 7, 8, 9. So 3. Yeah, it's not my n to the third is incorrect because 2 to the 3 is equal to 8. I had 9. What I mean to say is I think we have 3 times n factorial. Does that make sense? We have 2 times 1. No. Let me draw this out one more time. So we have 2 letters. Because right now I'm trying to think of the time complexity. So we have A, B, and C. And then 3 options for each of these. Right? And n is equal to 2. And what we had here is 3 times 3. So instead, this would be 3 to the n, the number of n. So we have 3n. That is our 3 to the n. That is how many combinations we would have. So that also equals our time complexity, big O of n. And the reason that is because for each letter we select 3 more possibilities. So our time complexity will be 3 to n. Ignore this. I'm just going through my options and verifying if what I'm saying makes sense. So 3 to the n is our time complexity. What about our space complexity? Well, we can decrease our space complexity by probably using backtracking. But I mean, it depends on if we're counting output or not, right? If we're not counting our output array, then yeah, if we're not counting our output array, then we would just have the cost of the O of n current stack, right? Because we're going to need some current. So I'm going to say if we're not counting the output and instead just using the individual array, we're going to call this O of n or space complexity, 3 to the n time complexity, O of n space complexity, and we'll use backtracking to keep this from being super large. So we're going to have a function, let's call it backtrack, and we'll pass. And then we'll need to call this, and that will give us our output. Our output will be in this array. I'm assuming we're not counting output as part of the time complexity, right? If I was assuming it was part of it, it would be through to the n, because we'll have through to the n possible answers. So I'm assuming we're not going to call it backtrack. We need our current position, our current digit that we're at. So we're going to have an index, and then we're also going to have our current output, okay? And what we can do is when the length of output equals 2, or equals the number of digits, then that's when we'll return. So yeah, so basically when index is equal to, if index is equal to the length of digits, which I'm going to just store out here. So normally I would do this differently, but if index is equal length, we're gonna append a copy of the current. Now what I was saying is we have through to the n outputs, right? But for every time we copy this into the output, that will take a time complexity of n. So n times 3 to the n. Space complexity will still be O of n, assuming we're not counting the output. So then what we do is for I in range, we start at this current index. Self dot length, because we go through all of these digits. Yeah. So we need to define the map, right? Num map, and we'll just define this here. So 2 will be equal to A, B, C. 3 will be equal to D, E, F. 4 is equal to G, H, I. 5 equal to J, K, L. Sorry, 6 is equal to M and O. 7 P, Q, R, S. Well, I guess I should correct this. It would be 4 to n, since it could only be 7, and it could only be 9. I shouldn't gloss over that. X, Y, Z. So these are our maps, right? So we have for each index, and then what we do is for letter in self.num map for that specific index. So then we would do cur.append letter. And then call backtrack with I, and then cur. But it should be the next index, right? Because we don't want to reuse that same. And I don't need this. Yeah, this should be for digit and digits index to the end, right? So we start at the second index. Okay, this is the part's incorrect. We just want to go for letter in the current digit position, digits index. We're just going to call this I for the sake of being shorter. We want to do I plus 1 to go to the next digit. That makes sense. And then we want to do cur.pop. So this is our backtracking part of the solution. And yeah, so we call it for each of these A's, or each letter at 2, so it'd be A, B, and C. And then we would go to the next one, call for each of those. And yeah, this is our map, and then our length we set here. Again, how this is done in an actual piece of code would be done differently. Like we would initialize this object, and we wouldn't alter that here. This would be initialized. But anyway, yeah, we're gonna do that. And time complexity, once again, is n times 4 to the n, and space complexity is O of n. The reason why there's this extra n here is because copying over this output takes time. It takes n time. Like, yeah, every time it'll be the length of digits. But the actual space complexity, if we're not counting the output, is this current variable, which at the most will be the length of digits. So now I'm just going to go through and verify that my output looks correct. We want a list of strings that make sense. I specified output as this. That'll be a list of strings. So I'm actually doing a list of lists. What we're going to do is just do this dot join current. And then this will be a string. It'll be different from the previous objects. This essentially is doing the same thing, but this gives us the output that we want. So now it'll be a list of strings. This needs to be changed to I because I switched that variable from index to I. Digit size is what we access. So digits is a string, so all of these should be strings. We call a backtrack, that's fine. We append the letter to current. And we also increment I. That looks good. This all looks good to me. Self is not defined. So since this isn't in the init function, that's why we're getting the error. What I'm going to do is just define this here. So what they're saying is string index out of range for 23. Why would this be incorrect? So we would do everything at 23. So this would be currently at 0. Oh shoot. So my num map is specified here. We have 2 and 3. We start at 0. 0 does not equal to the length, so we need to return here. Simple mistake. That's okay. That looks good. If digits does not exist, we want to just do this. If not digits, turn. And this should pass all the test cases. Perfect. Not too bad. Just another simple backtracking problem. You see a lot of those. I mean, all these backtracking ones are like basically the same. But hey, I'm recognizing that it should be backtracking and coming to the optimal solution. So that is awesome. But I am missing some of the edge cases. Like, yeah, that's frustrating. Like, I should do this if statement like before anything. let's do word search next. So word search, given a grid of characters,
Why are we committing?
given a grid of characters board in a string word, return true if word exists in the grid. The word can be constructed from letters of sequentially adjacent cells where adjacent cells are horizontal or vertically neighboring. Same letter cannot be used more than once. This seems like a classic DFS problem. We have these letters. We have A, B, C, D, E, F, G, H, I, J, K, L. So if we say this is our word, right? Like, how would we find this? If our word, let's say this, word search. Well, think about how you would do a word search just on your own. You would start at a letter. If that matches the first, like let's say our word is, yeah, A, J, K, J. We would compare these first two letters. Oh, that matches. So now let's look elsewhere. Let's start going down. That doesn't match the B. So then let's go to the right. And we see it matches the B. So then we mark this off. Then we see, look for a C. We check down, we check left. We already checked here, so intuitively we know don't look back here. But we need to have a scene variable in our function so that we don't do that. A scene set that marks the positions that we've already looked at. But we keep going. And yeah, so this will just be DFS, and I'm assuming we don't have to go diagonal. Let's check to see if they mention anything about that. Vertically neighboring, the same. So it only says horizontally and vertically neighboring. It says the same letter may not be used more than once. That, of course, means you can't use this position twice, but if the word has two A's in it, that's fine. And so, yeah, this will be a classic DFS. Worst case scenario is we have to loop through every single element in this grid. So that would be O of M times N. That would be the time complexity. The space complexity is also going to be O of M times N because we need a set of all the positions we've visited. But besides that set, we just need an index mapping where we currently are. And then we would just return like true or false immediately if we find the correct answer. So yeah, should be simple enough. Let's jump into it. So we're looking to see if a word exists. We know we're going to have a DFS function. And all that we will do is return that DFS function. But we can't actually do this from here. What we need to do is go through every single position, right? Like if I start DFS at A, that would happen to find the right answer. But let's say I started at E. I wouldn't find the right answer. And so I've got to start it from every single possible position that's valid. So I'll go through every single position. And then keep mistyping that. I'll go through every single position. And specifically, we only care to start searching if the character matches the first letter in the word, right? So if board ij word 0, then we'll start our DFS at ij and then an index of Yeah, 0. Because we can't assume we're at the second index, because we gotta look horizontally and vertically. Now, I don't know if word will exist. Okay, word will exist. It says word length could be just a single one, right? So this by itself, but that would be handled up here. So what we'll do is see if the first letter equals, and if that DFS returns true, we're going to return true. Otherwise, we'll have made it through every single letter in the grid, and we didn't find it, so it would be false. So this is the format that we're going to take. This is awesome. Now we just need to call DFS, okay? One thing that we'll need is a set, an empty set initially, of our scene positions. One thing of note is, well, we can mark, let's say, A as scene, and then B as scene, and C as scene as we're going through this, right? Like, let's say we go here, G as scene, K as scene, and that prevents us from going back to K and having an infinite loop, right? But once we mark this as not being finished, we can't mark these as scene again, because what if the word is actually starting at E? What if this is the correct starting point? We can't go up here and mark it as scene and say, oh, we already looked for this, because we have it. We could probably in some way store every single mapped out thing. That would be so space inefficient. So what I'll do is when we find something as false, we'll reset that scene set. That way when we start at E, like we'll reset what's been seen. So it'll look like this when we start at E. And then we would look through all of these again. We could probably come up with a way to use more space to reduce some of that repeated work. But that would be a lot of space. And also more complicated. So I would like to code this solution up first. But what that means is, yeah, the maximum space complexity is still this. But we aren't going through each of these only once. So this was incorrect. I think it's m times n squared. Because we have the potential to start here, look through everything, and then start at B and look through everything again. But that's DFS for you. So that will be my first solution, and let's see if we can do better afterwards. But to begin with, time complexity has been updated to this per my revision. Space complexity is still the same. So let's continue. So at the start of, I'm going to actually move this down here and set scene to be equal to an empty set right here. Reset this. Because we'll need to reset it when we start looking for a new character. So we're going to have our row and column position. And then we're also going to have our I position for the index in the word. And our base case will be if I is equal to the length of the word. If it's equal to the length of the word, that means we know we've already found the word. So we'll return true. Otherwise, we'll check to see if the position is in range. So if not, 0 is less than or equal to row, which is less than to length board, and 0 is less than or equal to column, which is less than length board 0. If this is not true, then we would return false. Or so if that is true, we would go to the next condition. Or board row column does not equal the current index of the word that we're trying to find. So basically, it's either out of bounds or the next letter does not match. If the next letter does not match, we return false. Otherwise, we go through and call DFS again. So I'm going to have an offsets specified here, and this will just be the vertical and horizontal positions that we'll go to. And I'll just do a for loop to reduce some of my repeated work. And so I'm going to have a row offset and a column offset in offsets. And then I'll redefine my row and column to be equal to the row plus row offset, column plus column offset. So now that these are the new row that we're searching for, what we can do is call DFS with those positions. And this would be I plus 1. And we want to specifically return this. Well, if this is true, return true. Otherwise, the default case would be return false. So I believe this is all that we would have to check. But now what I'm going to do, well, we forgot to add it to scene, and that's another condition here. Or board R, no, it would be or RC in scene. So if any of these are true, if we've made it through this far, we can add this position to scene. Scene dot add this tuple. Can I do better than just resetting the set every single time? I could add it and then just pop it, right? Returning here would be a problem though. This would work. I'm gonna not define this here and instead just do that directly in the loop. So is that all of the cases that could return false? Either it's already been seen or a next index does not match. Okay, then we add it to scene. I'm just gonna add this here because to me I like this more. If it goes through all of these DFS functions and doesn't find anything, then we'll return false. It's the same down here. All right. This looks good to me. Again, if the board is m times n, it'll be that time complexity squared, because we'll potentially have to visit each position for each spot. All those pass. We get a wrong answer here. Why do we get a wrong answer here? That is surprising. So what is the edge case that I'm missing? I'm going to do A, B, C, E, S, A, D, E. So they're saying A, B, C. S, S, A, B, C, E. Yeah, how are they finding this? A, B, C, E, S, F, S, F, E, S, A, D, E, E. And we need to start with A, B, C, E. I do that. A, B, C, E. So that would be A, B, C, E, S, E, F. I don't understand. Okay, A, B, C, E. That's where we start. S, E, 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 F. Okay, S, E, 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 F. S. Okay, no, that does make sense. Okay. So then why would this return incorrect? Okay, so what I'm doing down here with this scene set is incorrect. I should be adding it and popping it here. Dot remove. Small things. We won't have. Yeah, this should fix it. Yeah. There we go. It passes. Not a very efficient solution, but that's just the nature of the DFS problems. Some of this is probably calculating this again. So let's do I wonder how long I've been live. I'm about to go to the gym.
So, you guys may have heard that I'm doing a subathon, but this one's going to be a little bit different. Last year, I lost my dad to cancer, and ever since I've been looking for ways I could support people who are going through similar situations. So, we came up with the Fragathon. For the entire month of January, I'm going to be going live with a frag counter. For each elimination on stream, $1 is going to be going to charity. Subs and donations are going to be increasing this multiplier, making each frag worth more and more and more. But I won't be alone. I'm inviting all my friends to come by and donate frags in person at a LAN center that I'm building in my house. There's also going to be IRL events and challenges that are going to add to the counter when we're not gaming. In addition to the frag counter, 100% of proceeds from subs, donations, and bits will be going to an amazing charity. So I hope you'll join me in January to help raise money for a great cause in the most gamer fashion ever. You want to say anything to
Dear God.
any Polish fans that might be watching? You can just
Sure. You're lucky, dude. I had my fingers on the
Dziękuję, że go oglądacie i
I
brawa
was
dla
lucky I
niego,
was
bo jest
picking up my
dobry
face.
i dopingujcie.
Dang, this is like quick. For 23. Yeah, I don't know when it does its thing, but alright, I'm gonna go to the gym. We'll get back on the grind later.